Hello everyone, and welcome again to this continuation of our Process Safety Management Fundamental Training. Today we're going to be looking at element 6, which is Process Knowledge Management. I'm not going to go through our introductions again because this is probably the 6th session you've watched by now. So my name is Louise Whiting and I'm developing this course with Charlie Wigstrom. If you want to see our introductions, just go to PSM 101 online and you'll be able to see our introductions there. Did you know process failure costs, information scrap and rework costs, lost and missed opportunity costs are all caused by poor information quality? Now, if I was to miss the last bit of the sentence out, you would say that you would definitely want to prevent those. But time and time again, we see poor information quality on facilities, which can contribute to incidents as well as the things listed above. So we've seen this drawing quite a few times, and so I'm not going to go into much detail, but it's really exciting because we have entered the first element of understanding hazards and risks. This is the area that I'm most passionate about. However, without a good foundation in commit to process safety, you will be unable to understand the hazards and risks associated with your facility and then move on to managing them. As we discussed before, we have 4 elements on the bottom: commit to process safety, understanding hazards and risks, managing the risk, and then learning from experience. Each of these pillars need to remain strong to enable us to manage a good process safety management system. And without a good process safety management system, an incident can almost be assured. So what is maintaining good process knowledge mean? So the CCPS says that maintaining good process knowledge is developing, documenting, and maintaining process knowledge, and this forms part of understanding hazards and risk pillar. The knowledge element primarily focuses on information that can easily be recorded in documents such as written technical documents and specifications, engineering drawings and calculations, specifications for design, fabrication, installation of process equipment, and other written documents such as material data sheets. The term process knowledge will be used to refer to this collection of information. The knowledge element involves work activities associated with compiling, cataloging, and making available a specific set of data that is normally recorded in paper or electronic form. However, knowledge implies understanding, not simply compiling data. In that respect, the competency element complements the knowledge element in that it helps ensure that users can properly interpret and understand the information that is collected as part of this element. So we discussed already in element 3, I think, about process safety competence and how important it is to make sure you have the right competence at the right levels in the organization to understand your hazards. And here it is underlined again. If we don't have the right competence to understand this process knowledge, we are not going to be able to apply it when we need it. So the competence is really closely linked to this, and as I mentioned before, the pillars are not standalone. So we're going to now move on to what these different types of written technical documents and specifications might be, and show you examples of how things can go wrong if we don't have them in place. So let's move on to reviewing element 6. We're going to go again through a worked example. We're going to show you how to use the PSM tool to identify your gaps, and then we're going to show you how you might use the worksheets to close some of those gaps. We're going to watch a short video now.
Senator Collins, thanks for coming in.
It's a great pleasure, thank you.
This ship that was involved in the incident off Western Australia this week...
Yeah, the one the front fell off?
Yeah.
Yeah, that's not very typical. I'd like to make that point.
Well, how is it untypical?
Well, there are a lot of these ships going around the world all the time, and very seldom does anything like this happen. I just don't want people thinking that tankers aren't safe.
Was this tanker safe?
Well, I was thinking more about the other ones.
The ones that are safe?
Yeah, the ones the front doesn't fall off.
Well, if this wasn't safe, why did it have 80,000 tonnes of oil on it?
Well, I'm not saying it wasn't safe. It's just perhaps not quite as safe as some of the other ones.
Why?
Well, some of them are built so the front doesn't fall off at all.
Well, wasn't this built so the front wouldn't fall off?
Well, obviously not.
How do you know?
Well, because the front fell off and 20,000 tonnes of crude oil spilled into the sea caught fire. It's a bit of a giveaway. I just like to make the point that that is not normal.
Well, what sort of standards are these oil tankers built to?
Oh, very rigorous maritime engineering standards.
What sort of thing?
Well, the front's not supposed to fall off for a start.
And what other things?
Well, there are regulations governing the materials that they can be made of.
What materials?
Well, cardboard's out.
And?
No cardboard derivatives.
Like paper?
No paper. No string, no sellotape.
Rubber?
No, rubber's out. They've got to have a steering wheel. There's a minimum crew requirement.
What's the minimum crew?
Oh, one, I suppose.
So the allegations that they're just designed to carry as much oil as possible, to hell with the
ludicrous.
consequences, I mean, that's ludicrous.
Absolutely ludicrous. These are very, very strong vessels.
So what happened in this case?
Well, the front fell off in this case, by all means, but it's very unusual.
But Senator Collins, why did the front book fall off?
Well, a wave hit it.
A wave hit it?
A wave hit the ship.
Is that unusual?
Oh, yeah. At sea, chance in a million.
So what do you do to protect the environment in cases like this?
The ship was towed outside the environment.
Into another environment?
No, it's been towed beyond the environment. It's
Yes,
not
but
in the
into
environment.
No, but from one environment to another environment.
No, it's beyond the environment. It's not in an environment. It
Well,
has
it
been
must be
towed
somewhere.
beyond the environment.
Well, what's out there?
Nothing's out there.
Well, there must be something out
There
there.
is nothing out there. All there is sea and birds and fish.
And?
And 20,000 tonnes of crude oil.
And what else?
And a fire.
And anything else?
And the part of the ship that the front fell off. But there's nothing else out there.
Senator Collins, thanks for
It's a
joining
complete void.
us. Yeah, we're out of
The
time.
environment's perfectly safe. We're out of time?
Yeah.
Can you book me a cab?
But didn't you come in a Commonwealth car?
Yes, I did. But
What happened?
the front fell off.
So that was just a bit of fun. But actually that video was based on a real incident which happened off the coast of Australia. The ship had come into port and they were just about to load it with another load of oil. There was a lot of pressure from corporate to make sure that the ship went the next sailing so that it could get the money for the sailing. And on inspection, the crew found a crack in the deck. Now, the senator mentioned no paper derivatives used in the construction of the vessel. Well, they had used cardboard to cover up the crack and paint it over before the inspectors came. So the crack was not noticed when the inspection came before they set sail. The next one that contributed to this incident was the minimum manning. He mentioned that it was 1. Well, that the minimum manning on the ship was lower than what it should have been, and as a result, when they started to develop problems just before the wave hit it, they couldn't recover quickly enough. And then he mentioned something about what minimum standards. So the reason I've played this video for you is there's quite a lot of information here that should have been kept up to date, right? What is the required crew? That is process safety knowledge, which needs to be kept up to date. What roles do they need to do? What safety critical tasks do they need to perform? That is all really key data in deciding what the minimum manning is on your facility. The next one is what standards was it built to? You know, when do you need to do the inspection? How often might you need to do the repair? What would the minimum or maximum stresses be on the vessel? How should you ballast the vessel? Those are the things which will be held in the standards, and they should have been transferred to easily accessible process knowledge on the tanker. The final one is the repair, right? So when they had identified that there was a crack in the deck, and even whatever form of repair they had made, that should have been documented very clearly so it was easy and accessible. But in this case, that didn't happen, and as a result, we had the incident off the coast of Australia. So we're moving on now to our worked example. So this example, as always, is going to show you why process knowledge is important, why it needs to be easily accessible, etc. And then we're going to go through how to use the tool to identify the same issues in your facility and how to formulate a closure plan using the tool. So we're going to watch another video now.
On December 19, 2007, a powerful explosion and fire occurred at T2 Laboratories, a small chemical producer in Jacksonville, Florida. The blast killed and injured workers, destroyed T2 Laboratories, and extensively damaged 4 nearby businesses. Windows blew into offices, striking workers with flying glass.
The explosion at T2 Laboratories is one of several accidents that the CSB has investigated caused by runaway chemical reactions. Accidents resulting from reactive hazards occur too frequently and often have serious consequences.
Behind me on this concrete pad, there used to stand a structure some 50 feet high that had a reactor vessel in it, in which the company that operated here, T2 Laboratories Incorporated, manufactured a chemical known as methylcyclopentadienyl manganese tricarbonyl, or MCMT for short. The entire structure and reactor vessel were blown away in the explosion.
T2 produced MCMT, a gasoline additive, in batches using a 2,500-gallon reactor. An operator controlled the process with a computerized system in a nearby control room. In the first step, liquid chemicals and sodium metal were loaded into the reactor, heated, and then mixed with an agitator. The reaction produced hydrogen, which was vented to the atmosphere. In normal operations, when the temperature reached 300 degrees Fahrenheit, the operator would turn off the heating system. But because this reaction was exothermic, or heat-producing, the temperature inside the reactor would continue to rise. At 360 degrees, operators would begin to periodically fill the reactor's cooling jacket with water. As the water boiled, heat was removed, controlling the temperature. However, on the day of the accident, the CSB found that the operator tried to cool the reactor as usual, but the cooling system likely malfunctioned, perhaps due to a blockage in the water supply piping or a valve failure. The temperature and pressure inside the reactor began to rise uncontrollably in a runaway chemical reaction. T2's co-owners returned to the plant after a worker called to report the cooling problem. While one owner searched for the plant mechanic, the other went to the control room. Concerned about a possible fire, he warned employees to move away from the reactor. Inside the reactor, the pressure was still increasing, reaching 400 pounds per square inch and bursting the rupture disc. Witnesses heard a sound like a jet engine as high-pressure gas began to vent from the reactor. But it was too late. Within 10 seconds, there was a massive explosion, equivalent to about 1,400 pounds of TNT. The blast damaged buildings over 1,500 feet away. Debris rocketed up to a mile. The co-owner and the operator in the control room were killed. 2 operators further away died from flying debris. 32 other people were injured, including 28 at nearby businesses.
This facility housed multiple types of chemicals. That was a kind of a mass storage of everything you can think of, and it was all mixed together and it was all burning together. And for our perspective from the hazardous material side, it makes kind of a worst case scenario.
Damage from the explosion was so severe, 4 nearby buildings were condemned.
My office personnel heard a whistling sound in the area, and as they looked out the window, they saw an orange glow, which was the blast coming off of the explosion, and it came to our offices, and it blew in all the windows in our office trailers. Immediately, it was a shock or a surprise, and then all of us were shaken afterward.
In 2002, the CSB completed a study on reactive chemical hazards. The study identified 167 serious accidents involving uncontrolled chemical reactions between 1980 and 2001, causing 108 deaths and hundreds of millions of dollars in property damage.
When mixing chemicals that have an exothermic reaction, You need to be aware of the amount of energy that could be released by the reaction to prevent vessels from bursting like the one that happened here.
T2 developed its MCMT process using a 1-liter reactor. The company then scaled up the process directly to full production volume in the 2,500-gallon reactor. After 41 batches, T2 increased the batch size further by 1/3. As the scale of the reaction increased, effective cooling became ever more difficult. During 175 production runs making MCMT, T2 periodically experienced problems, such as unexpected temperature increases, but the company never fully investigated the causes. And T2 had only equipped the reactor with a simple cooling system using city water. When the system malfunctioned, there was no backup cooling immediately available to control the reaction.
The most important thing to managing reactive chemistry hazards is that you have to have a thorough and complete understanding of your chemistry under design conditions and also under all foreseeable abnormal conditions.
The CSB has noted that to prevent reactive chemical accidents, companies should identify and thoroughly evaluate reactive hazards in their processes, implement appropriate emergency pressure relief systems and other design safeguards, develop effective operating procedures and training programs, and carefully manage any changes to existing processes, and plan for possible accidents, including evacuation drills and emergency response exercises. Although T2's owners had undergraduate degrees in chemistry and chemical engineering and experience in the chemical industry, neither had been trained on how to recognize or control reactive hazards.
A large portion of the incidents have occurred because the people who are actually running the process were not aware either of the existence of the reactive chemistry hazard or of the potential magnitude of the consequences associated with that chemical reaction hazard. So a lot of the problem, I think, is education and awareness.
The board noted that multiple sources of information are available on how to control reactive hazards, including publications from the Center for Chemical Process Safety, the Design Institute for Emergency Relief Systems, and the UK Health and Safety Executive. Following the T2 investigation, the CSB recommended that the American Institute of Chemical Engineers work to incorporate education about reactive hazards into college-level chemical engineering curricula.
Reactive chemical hazards continue to be a too frequent cause of chemical accidents. Improved industry practices and increased education will help prevent these tragedies. Thank you for watching this CSB safety video.
So that video was quite graphic, and there were quite a few fatalities from that incident. A couple of things that came out in the video were that the relief valve or the bursting disc opened before the vessel ruptured, but after only 10 seconds the vessel ruptured. This indicates to me, and after having read the incident report, that the bursting disc was not sized for this reaction, which occurred exothermically and uncontrollably. Having read the incident report, the first batch of the batch testing in the laboratory of this reaction didn't actually require any cooling at all. And as a result, the cooling was only identified when they scaled up the reaction. Remember, they scaled up from 1 litre to 2,500 gallons, which is a significant scale up. When they scaled up, they realized they needed cooling. Now, the main reason for this is because the surface area to volume in a 1 litre vessel is much higher, and therefore the transfer of heat to the surrounding is much quicker than when you scale it up, because there's a larger proportion of the fluid which is not in contact with the outside. So anyway, they identified they needed cooling, but another thing that happened when they were doing the batch testing in the lab is that they didn't let the temperature increase above 380 degrees Fahrenheit. On the day of the incident, the temperature increased above 390, and in this case, a second exothermic reaction happened, which was much more energetic than the first exothermic reaction, which is the one that resulted in the overpressure of the vessel. Now, the CSB found that regardless of how they designed that vessel, there is no relief valve for that size of reaction, for the size of batch they were running. There is no relief valve which would have been sufficiently large and quick acting to relieve the pressure built up as a result of that second exothermic reaction. The safest thing would have been for them to have sized the relief device, or the bursting disc in this case, to relieve at 75 psi instead of 400 psi gauge. This would have allowed one of the reactants for the second reaction to boil and evaporate, therefore not being able to be consumed as the temperature increased in the vessel, therefore meaning that the second reaction didn't happen and the explosion wouldn't have happened. Now, I'm going through this because there's some key process knowledge which was missing in this facility. The first is actually really understanding the reaction chemistry, and that was one of the things that was noted on the video, that there is often a significant misunderstanding about the reaction chemistry. You need to really think about what reactions could occur, both during normal operation as well as during deviations. Now, one of the problems here was they never identified a HAZOP as being a requirement. That we'll cover it in the next lesson when we go to managing risk. But they never identified a HAZOP as being one of the requirements for this facility before it came into service. And as a result, they didn't think of any of the deviations, like cooling water not operating. So as a result of that, they then didn't think that the reactor could exceed the temperature which was used during testing. Now, when the CSB did the same tests with smaller volumes, but they allowed the temperature to increase above 390 degrees Fahrenheit, on each of those, the small reactor that they were using in the lab ruptured. There was no way of relieving the pressure quickly enough so that that didn't rupture. That reaction was so fast, generating so much vapor, it was unable to relieve. So if they had identified loss of cooling as a potential cause, they could have re-examined it within the lab before they scaled it up. Then, if they didn't identify the lack of cooling as a potential, well, they could have maybe identified the failures on the cooling water system. So, despite having operated this vessel for a significant amount of time and having a large amount of water evaporate during batches, they had done no preventative maintenance on the cooling water system. Now, if you remember from the video, they said that they were using city water, which just means the water that you and I get from our taps. They were using city water to cool the reactor, which may have been alright, but city water will contain some minerals which, when evaporated, will deposit on the walls and on the valves in the system. This is one of the likely causes for the valve malfunctioning during opening of the cooling water to the reactor. So they were not able to get cooling water to the reactor because they didn't consider one of the key process safety knowledge parameters, which is the composition of the water which they were using. And then considering that under the conditions they were using it, where they were evaporating it, leaving the minerals behind, clogging up the system. And then the other things that, with regards to process knowledge, was the area, the surface area for which heat transfer could occur. the potential for fouling, which obviously was very real given the water they were using, and the fouling would then have reduced the heat transfer between the cooling medium and the reactor. The size and scale of the reaction. So we heard that it was at 2,500 gallons, and then it was scaled up by a third. There's no evidence that the CSB found of them documenting why they scaled it up, how they scaled it up. Did they consider any additional safeguards required? Another key sort of information would be thinking about the failure frequency, which would be one of our key process knowledge, of the valves in this type of service for the cooling water, considering it was a key safeguard. This wasn't considered because it was never identified as a key safeguard, and as a result, the protection measures was only one cooling system. Now, given the severity of the consequences, how far-reaching the consequences were from the site, you would think that if they had known that, they would have put in at least 2 layers of protection to protect them against a potential loss of containment. But they didn't identify that, so there were quite a few sort of fundamental gaps in their process knowledge when they designed and scaled up this plant, which meant that the decisions they made led to the incident. If you don't have the right information upon which to make the decisions, there is a good chance that you will make the wrong decisions and result in dangerous consequences later. The final one, which they could have learned from in hindsight, is that they had actually more than 3 runaway reactions happening in the previous batches. So they knew already that inadequate cooling was a problem on this vessel, but yet they didn't do anything to remedy this before the batch that they undertook on this day. So now we're going to move on to what the different elements are in maintaining your process knowledge. So the first one is maintaining a dependable practice. The first element under here is consistent implementation. This requires, as I've said before, a documented way in which to apply things. If everybody knows what they need to do, they're trained to what they need to do, and it's very clearly documented, people will do it. If it's kind of guesswork, kind of think, oh, well, maybe this is what somebody else did, it's not going to happen. So making sure that consistent application happens is making sure that everybody is trained and it's very clearly documented. Secondly, we need to define the scope. So what is process knowledge for your facility? Do we need to know about the water chemistry? In this case, it was key, but in your facility, it might not be important. So making sure you know what the scope of process knowledge means for your facility and defining that so that you make sure that you store your knowledge appropriately. We need to thoroughly document chemical reactivity and incompatibility hazards. So in this case, as you saw in the video, chemical reactivity is not very well documented. Understanding the reaction is not very common, and this leads to major incidents. Now, this is not a lack of information being available as to how we can understand this, as we saw in the video. The problem is people are not accessing that information so that they can understand. So, and then the second one also happens time and time again in incidents. Only this year in 2020, there was an incident in India which resulted from incompatible materials. Now, the way that I manage this on sites is I just say to guys, look, just forget we have procedures, forget everything. What happens if all of the chemicals, each one of them, was matched with any other chemical we can have on our facility? And then once we've had a look at those systems, we decide which ones could introduce a hazard. So for example, we might have chemical A, which is stored on site 1, and we might have chemical Z, which is normally stored on site 4. Well, we could say, hey, well, these two chemicals aren't able to be mixed because they're stored on different sites. Fine. That will be our assumption in our hazard assessment, that these two chemicals will never be stored on the same facility, they will not be transported in the same truck, and they will not be stored in drums which look the same, and so therefore there's no potential that it can be a mistake. However, if any of those assumptions are incorrect, there is a potential that the wrong barrel could be loaded off at the wrong facility and there could be a mix. So making sure that you really look at everything, deciding which ones introduce a hazard, and then defining what your assumptions are either. Or if you think, okay, maybe we can't assume that they will never mix, then defining what your safeguards are. And making sure that those are implemented on your facility can really save you from incompatibility hazards. Now, in the best case, incompatibility hazards mean that you need to throw away product or those chemicals. In the worst case, it can result in, as we saw, this exothermic reaction, which can result in overpressure and explosion. And in another case, it could result in release of toxic gas, which is very common in incompatibility hazards. The final one under maintaining a dependable practice is assigning responsibilities to competent personnel. Now, if you assign the responsibilities to managing this data to people who are not competent, well, you may or may not get a very good database which is easily accessible and has the right information. Worst case, you don't assign it to anybody, and then you're definitely not going to have a database which is easy to access and up to date. So making sure you assign it and it is to someone who's competent. Competent again comes through in each of these elements, as you'll see in the future ones, making sure that people are competent to do the job that you're asking of them. The next one is cataloging process knowledge in a manner that facilitates retrieval. The first element here is maintaining information available and providing structure. So once we have all the information in one place, that's not the end of the story. Things change, information develops about how to manage all the hazards, so we need to make sure that this information is kept up to date. We need to make sure that we provide a structure first for where to store things, how to name them, and how they will be retrieved, and then secondly, a structure for how to put information into this database, right? So there's two types of structures there. The next one is protecting knowledge from inadvertent loss. So if we're storing everything in paper, making sure that we don't have all the paper copies of everything and there's only one paper copy and that is available in one place. If we had a fire, they are all lost. Making sure that we had a backup copy somewhere else. Nowadays, things mainly are stored online in databases. We need to make sure that they can be stored somewhere safe. That means that we don't store everything on one hard drive. If we have to store something, we back it up. And if we have to store something online, we make sure that that is a secure connection and so that nobody else could come and interfere with our data and maybe lose it on our behalf. Store calculations, design data, and similar information in central files. I've been on several facilities where the calculations have not been handed over from the contractor. So we go to make a modification or we want to check something and all we have is the data sheet. We don't know what assumptions they made. We don't even know which calculation they used to get to the answer they got to. So we have to start from scratch really. Now this might be okay for something like a relief valve, but when you start to think of something like a quantitative risk assessment, which has many assumptions, many calculations, you're starting to see that we're just having to redo the exercise, having to redo the whole quantitative risk assessment, which is a significant cost to the facility. The final one in this category is documenting information in a user-friendly manner. Now, if the information is all documented in a format which is really difficult to read, or it's in a format where you have to download a special software, the software doesn't last, you need to download it again every time, all of these things can be barriers for people to actually using your process knowledge. If people don't want to use it because it is difficult to access, it's going to be the same as if it wasn't there. So making sure that it's easy to access is really important. We're moving on to the next category, protect and update process knowledge. So the first one is control or limit access to out-of-date information. Now, in some cases you might need to see the previous revision of a document, but that should not be the document which comes up in your search. So for example, I was on a facility and they were having a lot of problems with the heat exchanger. It was just not cooling the way that we needed it to cool. We had 2 trains. One train was working fine, the other train was not working fine. So it was a case of investigation. Why was this train not cooling? It didn't matter how much water we put through. We were even opening the bypass valve to get more water across the heat exchanger. It was not working. So had to look back and to see what could have happened. So I went back to basics and said, okay, well, let's check the area. So the area of the heat exchanger was good in accordance with the data sheet. The heat transfer coefficient was good. It was the same material. But actually, when I dug deeper, it turned out that there was a step change from one shutdown to another shutdown. And in this shutdown, the bundle for that heat exchanger was changed. And when they changed it for a very slightly different material. It was still stainless steel, but it was a different grade, which had a different heat transfer coefficient, which significantly changed the amount of heat transfer that could occur over that area. And as a result, the heat exchanger was undersized. The next one is ensuring accuracy. So how do we make sure that this documentation is accurate? We need to make sure that it is, number one, when we do the design, that it's there. When we do the purchasing, those documents are accurate and updated. When we do the commissioning, if any changes have occurred, those changes are reflected and the commission documents are uploaded and they are accurate. And then when we are doing operations, maintenance, and any changes, that all of those are changed on the key documents and they are kept accurate, which means we need to have a really good review and approval process for our documents. Just the fact that Joe Bloggs comes and sends the document controller a document doesn't mean the document controller should put that document in your database. He needs to check that the right authorities have reviewed and approved that document. Otherwise, he sends it back to Joe Bloggs and say, hey, you want to update the PNIDs and you haven't spoken to the process engineer? Come on, man. So he goes back, he checks with the process engineer. Once the process engineer approves, then it can be uploaded. The next one is protecting against inadvertent change. So especially with online documents, it is really easy for people to inadvertently change something. And that could be something as simple as completing a spell check on a document, right? How many times have you completed a spell check on a document and then you read it and again you go, what does that mean? Because they've changed words in there which maybe don't come up in the spell check, which are not part of the normal language, but is required for technical understanding of your document, and it's just a different way of spelling something, or it corrects it to the wrong thing. So making sure that there's no potential for inadvertent change of your controlled copy, the copy that everybody will be working from. Yes, we may need to change it, but in that case, we check out the document, we change another version of the document, and then we give it back to the document controller once it's reviewed and approved, and he updates it in the database. Next, we're going for protect against physical or electronic removal or misfiling. So I know that when I go around and clean everything up in my house, everybody goes, where's this? Where's that? I can't find this. I can't find that. It's really easy to put things away where you think everybody will know where it is and they don't, right? The same is true for documents. If someone has a tidy up, or maybe somebody has loaned a document from your document library, the physical library, and not returned it, it's very easy to lose things. Now, in an electronic world, it's even easier, right? At least you could have somebody there looking to make sure nobody took any of the documents out of your library. In an electronic world, it's much easier, right? You just click of a mouse and inadvertently you've moved a whole database to another file. So making sure you have some safeguards in place to prevent that from happening is really critical. The final one in this section is support efforts to properly manage change. So as I said, change is going to happen on your facility. It is an inevitable truth. Making sure that you have proper procedures in place for 2 parts of the change. The first one is, how is change actually going to be reflected in your documents? Are you going to use triangles? Are you going to use clouds? Whatever that is, how are you going to reflect the changes? And making sure that there's a very clear process for how the document will be changed, approved and checked, and then uploaded into your system. right? So that's the first element of change. The second element of change, which is I've seen fall down many times, is people don't actually identify which documents need to be changed. So having a real clear way of defining how to identify the documents that could be changed and how to engage with the right authorities so that they can check whether that document needs to be changed is critical. We'll cover more on management of change in one of the later webinars. We're moving on to the last one, which is using process knowledge. So we need to ensure awareness, right? People need to be aware that this process knowledge is there and that they can use it, and what type of knowledge it is, how they can find it, how they should not use it, i.e. they should not be changing things, etc. Making sure that there is awareness of your process knowledge, where it is, how to use it, is really key to making sure that people do use it. And the second one is ensuring that process knowledge remains useful. If your process knowledge is out of date, doesn't reflect what's on the facility, people are not going to use it. It is not useful for them. They will then have to go and find it somewhere else. Making sure it maintains a usefulness is really key, ensuring that people use your documents when they need it. And for example, there are a lot of facilities which used to have paper-based systems, right? And now with things being easier with electronic things, they have moved over to an electronic database. But some facilities haven't. And as a result, people will sit behind their desk, they will search what is available on the electronic database, and if the other bits are not available, they may not look for them. Number one, because they might not be aware that the paper parts still exist, and number two, they may just not have time to look for them. So making sure that you make things as easy as possible and review regularly is key.